Okay. Um, Sorry for the delay. I've had internet problems this morning, so that's a bummer because um, so hopefully the internet doesn't drop in the middle of this broadcast. If it does, I will stop and restart and then put two videos up if needed. Anyway, um, we don't need the paper just yet, although I am going to write 2 words on it. So we're going into the next phase of linked lists. Um, but before we do that, I want to spend a little bit of time talking about dynamic things versus static things. Dynamic things, you're going to see lots of. I know you can't read that. Let me see if I can move the camera a little closer. Dynamic things are going to show up in your code with lots of pointers associated with them. So what we focused on last week was really just the getting comfortable with the pointers part. And then sort of the introductory parts of building a linked list. But a linked list is a dynamic data structure, and I want to talk a little bit about what dynamic means versus what static means. Up to this point in the semester, you haven't done anything that, well, before last week that wasn't static, basically. So I have lab 11 pulled up, but I'm going to do a different piece of code to talk a little bit about the difference between dynamic and static things. So let me close that for a second and start up a new file here. So I'm going to write a little bit of C++ code here, and I'm going to do some dynamic things, and I'm going to do some static things. And then I'm going to build up, I'll do it as a class, just for, yeah, sure, just because I feel like doing it that way. So I'm going to create a class, and then I'm going to create the driver to test it out just right in the same file. Today is April 14th.cpp. Okay, so I'm going to make a class, and the reason I'm doing this is so that we can use the class to experiment with what does it mean for something to be static versus something to be dynamic. So I'm going to create a constructor here. I haven't decided quite what to do with it yet. Yeah, I know what I'm going to do with it. Need to include string. Okay, so the whole reason I'm building this class box is because I want to use it to show you how static and dynamic things work in C++. When we're doing a linked list, there's going to be a lot of dynamic things, and the way you make things dynamically in C++ is using pointers and the keyword new and the keyword delete. And you're going to see me do all of those things here in this example. So I'm just going to make a sloppy little class. I will call it box, and I'm going to make a constructor inside of it. But I'm also going to do an output here. So we can see when boxes are actually created. Okay, so I'm going to make a static box. I'll put apples in it just because that one's easy to type. So this is a static object. B, I'll call it B1, is a static object. The reason I know that is because I don't see the keyword new anywhere, and I don't see any pointers anywhere. So I don't see any of the clues that would tell me this is anything other than a static object. Now a static object, the whole trick to static objects is that they are created and destroyed automatically. Effectively, the compiler kind of knows when to create them and when to destroy them, so it just builds the mechanisms to do that. I'm also going to set up for a dynamic box. Which I'm going to set to null. And what I want to show you here is that only one box is going to be created, and that's the static one. You just sort of have to get used to what this feels like. Static things are created and destroyed for you automatically. Dynamic things, you have to manually create and destroy them. So this is a pointer, and a pointer is not a box. So I'm only going to see one box created. It's going to say box apples created when I run this program. I did not put that in the same place, did I? I didn't. Okay, so let me run this program. So you'll notice that only a box of apples was created. I didn't sort of do anything other than use the constructor with contents to build it, but otherwise it was kind of created for me statically. So static means that you're not manually having to do anything to create it other than declare it, and you're not having to do anything manually to destroy it, because it'll be destroyed for you. Now the way that you show things are being destroyed, hold on, I'm going to put glasses on. The way that you show that things are being destroyed is there is a special function called a destructor that every class instruct has. They're like constructors, except for there can only ever be one destructor. Constructors, you can make many different versions of constructors for one class, but the destructor can never be only than this one thing. But all I'm going to do is box, and then I'm going to print out its contents. Destroyed. So we can see when it's destroyed. So what I'm saying here is that this static box is going to be created automatically. We saw that, but if you watch here in a second after I compile it, you're going to see this output. And the reason why you're going to see this output is because this box, this static one, is going to automatically be destroyed for me. So it'll tell me that the box of apples has been destroyed when that happens, because I've made an output to do it. So there it was, destroyed. Why and when was it destroyed? Well, because it's static, C++ chooses when to destroy it. It uses the basic scoping rules in C++. So the block inside which the box was created, when that block passes out of scope, which in this case is the program coming to an end, then anything static inside of it is destroyed. I'll show you another example. I'll just make a function f. I'll put a box here. I'll put a box of functions, and then I'm going to call f down here. This is a lot easier if we were face-to-face in lab, because I could see what your faces look like and stuff, but what's gonna happen is the program's gonna run, it's gonna hit this line first, and B1 is gonna be created, and I will see box contents created when that constructor runs. This one doesn't do anything. It just creates a pointer to a box. It doesn't create a box. It doesn't destroy a box. There's no box. It's just a pointer, kind of like my finger's a pointer to a person. Well, my finger isn't a person, but I can point it at a person. And then F is going to happen, and when F executes, I get into a new scope, this block. And inside of this scope, a box is created. So we're going to see that. Right after the box of apples is created, the box of functions is going to be created. And then that function is going to come to an end, and at that point, the box of functions is going to be automatically destroyed. Why? Because B inside the function is a static box. So it will be created when C++ first encounters it, and it will be destroyed when the scope that it's in exits. So when we leave this function, B will be destroyed. And you'll see that. A box of apples will be created. Nothing will happen for the pointer. And then F will execute. It will create a box of functions, and then F will end, and it will immediately destroy a box of functions. Then the program will end, and it will destroy a box of apples. So there's the apples created, there's the functions created and destroyed in F, and then apples, finally, its scope exits, which is the main function, and it's destroyed. So those are examples of static things that are created and destroyed for you. Let me move this box pointer. No. Yes. No. I don't feel like moving it. All right, so now let's talk about dynamic. So when we say dynamic, we mean that you are manually creating things. You're not letting them be automatically created for you, and you are manually destroying things. And they go together. So I'm going to take this pointer, and I'm going to make something dynamically with it. And the way you do that is with the keyword new. So when you see new, what's happening is you are manually, dynamically creating something. I'm going to dynamically create a box. I'm going to put pointers inside of it. So that's going to cause, that's that constructor. So it's going to say box of pointers created. Now when you do something dynamically and manually, it's not cleaned up for you. Static things are automatically deleted, but dynamic things are not. So what you're going to see happen is the apples will be created, the pointers box will be created, then it will go into the function F, where it will first create a box of functions, and then as it leaves F, it will destroy the box of functions. And then the main function returns, and it's going to destroy the box of apples because apples is static. What won't happen is that the box of pointers will never be destroyed because it's a dynamic thing. It was created with new, and when you create something with new, you have to manually destroy it. So let me recompile that. So there's the apples created. There's the pointers that I dynamically created. There's the static box of functions that's created and destroyed in the function F. And then there's the box of apples, which is static, and it's destroyed at the end of main. So notice here that dynamic things are not automatically destroyed for you. The way you get rid of dynamic things is with the keyword delete. And notice, by the way, I'm deleting and calling the pointer that I used to create the thing. So new and delete go together. This is a cool thing about C++, and it's also a thing that leads to lots of mistakes in the world. It's very easy to make dynamic things with new and then forget to clean them up after yourself with a delete. In our class, it usually doesn't have significant consequences, but it's one of the, I would call, a weakness of C++ that you can make this mistake. And in fact, the program that I just compiled and ran, I purposely made that mistake. So now what you're going to see happen is the static box will be created. Now I have a pointer available. I use that pointer to dynamically create a box that pbox1 points to. Then it jumps out to the function and creates and destroys a static box. And then finally, my manual delete will cause the box of pointers to be deleted before the static box of apples at the end is deleted. It's a lot of stuff to take in. You don't have to write that much code to explore the idea. But one thing that I recommend you do is like make one of these boxes for yourself and do lots of news and deletes with it and see what happens. So let me build that. So there's the static box of apples created. There's my dynamically created box of pointers. And dynamic really just means that I use new to create it and have a pointer to it. And that also means, though, that I have to use delete to get rid of it. Here's the function f that creates and automatically destroys a static box. Here's me manually destroying my dynamic box of pointers. And then finally, the box of apples being automatically destroyed when it passes out of scope, when main returns. So that's hairy stuff. Okay, so that's sort of step one. Step two, I'm going to go back through some of the lab from last week, which is also included in this week's lab, and then just hopefully with the repetition of it, it will help. So this dynamic stuff, some people will call this memory management or manual memory management. But the keywords new and delete in C++ are you, the programmer, deciding when to create things. And then that also sort of gives you the burden of figuring out when they need to be destroyed with the keyword delete. So new and delete. Why do we do this? So I'm not going to do a full program, but why do we do new and delete kinds of things if it's bad for me to forget to delete? And it is bad to forget to delete, by the way. That's called a memory leak, which you don't want. But the reason why we do it is because it gives us a lot of flexibility in terms of the amount of data that we manage. So if you think, I don't need to code this actually. If you think about a playlist and a music playing piece of software, if you use arrays to represent a playlist, how many songs, what size do you make that array be? 1, 2, 1,000, 1,000,000? The problem with trying to figure out in advance so that you can use a static amount of memory is that it's highly variable piece of information. Some people's playlists might have 3 songs, someone else might have 300, and it's not practical in programming to, what do you do with that? Do you guess low or do you guess high? And so in C++, we have dynamic memory that allows us to only expand out the use of memory as much as is needed. So we could, every time they add a song to the playlist, we make a dynamic allocation for that song entry on the playlist. And then the playlist is never any bigger or smaller than it needs to be. It's exactly the size that we always need it to be, because every time we get a new entry, we dynamically allocate memory for just that new entry. And then we can also use the delete keyword to destroy the memory and free the memory for that entry whenever they remove something from the playlist. So it's kind of a crude explanation of why we have that technique. But let me kind of start on this week's lab by redoing some of last week's lab. So if you look at this week's lab, it's the same as last week with 2 exceptions. And it's expected, and what you ought to do is take the lab that you did last week and just add new stuff to it. If you need the practice, by all means reinvent the wheel, but you don't have to. You can just take what you did last week. But let's see what's new here. So the constructor for singly linked lists, that's not new. That was there last week. Here's a destructor. So we just talked about destructors. So now we're actually going to implement one, and then so that we can handle the situation where we're dynamically allocating memory for nodes. So every time you see the keyword new, something dynamic's happening, which means that we need somewhere to have the keyword delete to destroy the memory associated with that dynamic thing. So destructors is a mechanism to do that. Pardon me, I'm burping into the microphone. Push front we had last week. Pop front, that's new. But that's destroying a thing. So if you look at the new stuff we're doing this week, it's all about destroying things. We have the list destructor. We have pop front, which destroys the first node in the list. And we have the clear function, which destroys all the nodes in a list. So that's the new stuff, is all about destroying things. So for the next 15 minutes or so, I'm going to re-implement last week's code and talk about the dynamic stuff as I'm doing it, and then maybe we'll add one function of lab 11 to the mix. So let me grab all these functions. This is slist.h, so I'm going to do my implementation in slist.cpp. I think I remember what everything's. Yeah, I'm going to leave the comments for now, just to be sure. I'm going to go through my usual process of class name, : and then I'm going to put that on the front of every function. So notice the destructor looks funny because of that tilde, but that's the function name. You don't actually ever call that function, by the way. Delete calls it for you. Delete is the way that you invoke it. Static things automatically invoke the destructor for themselves. Okay, so that's the function name, I'll get the slist : on the front of them. And then I go back and I put the blocks and I stub them out. The constructor and destructor are funny looking because they don't return values. But that means also that stubbing them is easy. Push front is void, so stubbing that is just an empty block. Stubbing pop front is just an empty block. Stubbing front needs to return an integer, so I'll return 0. Stubbing get size needs to return an unsigned integer, so I'll stub it with return 0. Empty needs a bool, so I'll just stub it with return false. Clear is void, so empty block to stub that. And then to string returns a string, so I'll just return an empty one for starters. Okay, so I'm going to go and kind of do some re-implementation and speak in terms of where I'm doing dynamic things. Okay, so the constructor, I didn't bring the notes for it. What did the notes say? Okay, so initializes head to null, size to 0. So pointer in this size equals 0. So size is the number of nodes that the list is currently tracking, which would be 0 to start. Head is the way that the list tracks the first node in a chain of nodes, which initially is going to be pointing to no nodes, which is null pointer. Not going to worry about the destructor for now. Let's do, well, what does it do? Invokes clear. All right, we'll come back to that. Let's see what else was easy. Well, let's just go down the old ones first. So push front. So adding a node to track in a list is a matter of dynamically allocating a node to hold a value. So here's the pointer, node n, and I'm going to dynamically allocate a node to hold a value. So that is a dynamic allocation with the keyword new, which means technically if somewhere I don't delete this thing, I have a problem. So this week's lab is about addressing this issue where we're dynamically allocating a thing, but we never actually use delete to destroy it. I'm using the nodes constructor, by the way, which is in slist.h. Here's the nodes constructor. The node constructor takes a value, actually nulls out the node's link pointer next, and then assigns a value into it. So I make a new node, and then I use its link pointer to point to whatever is presently the first node in the list, because I'm about to place this node in front of the old one. I can show you on the vertical cam. We saw this last week, but I'll draw it again. So this is the initial state of the list. This marker that the list keeps to keep track of that first node is null to start, which means there's no node there. So what I'm doing with push front is I'm putting a node right in the front. And if I were to push front again with the second node, then I want the second node to be in front of the first node. So push front is always, something's, oh, I see it. Push node is always adding the most recent node in front of other things. Okay, it's a quiet group today. So just so you know, push front means take whatever just came in and tack it on to the front, and then the list itself needs to be aware of the fact that, oh, this most recent node is now the first one, and the ones that came before it are now chained together. So I make a new node dynamically. That new node, I take its link pointer and I point it at what used to be the first thing in the list. And then now I take this marker and I say now point it at the most recently created one. Which is a lot easier to sort of gesture in a classroom. But that new node's link pointer, I'm pointing it at, when you see an assignment with the pointer, so n's next points at is a way to understand what this equals means. Points at the list's current head. So in this case, for example, if n has a 2 in it, then n next at head points at the 1 because the 1 used to be first. And then I take this marker, head, and I point it at, take head and point it at the newly created node, n. Shift head over. I also need to make sure that I grow the size by 1 because I just added a node. I need to make sure that I'm keeping count of how many I add. So I did that function last week. I just wanted to point out to you that there's a new in there because I did. I dynamically made a node. So this is one of the things that's useful about a linked list, is that it's just as big as it needs to be always. And if you need to put more data in it, then you dynamically allocate a node for that data and then attach the node to the list. So lists are always exactly and never more than exactly or less than exactly. They are always exactly the amount of space that you need to store the data that you have. The purpose of a node basically is just to give us the ability to chain these pieces together so that we don't lose a piece. Okay, we didn't do pop front. We did do front, so I'll go ahead and do that. I'll just remind you that empty list. So if this list is empty, you can call functions that way. But usually, well, that's fine. Anyway, if the list is empty, then throw this thing. You can't get the data out of the first node in the list if there's no nodes in the list. There's no nodes, there's no data, and you're left with this situation. There's not much you can do other than throw up your hands and say, I can't give you data, there's no node. But if that doesn't happen, then you can return the data from the node that the head is currently tracking. So I go to the head node, and then I go inside that node and I get the value and return that. That's what this function is supposed to do. Let's see, get size. So get size is this size. That's all, just how many nodes are you currently keeping track of. Empty is really a, if the size is 0, then there's no node, so that would be an empty list. That would be true. I'm not going to mess with the string one right now because I don't feel like that. Okay, so, but now let's look at, let's start up one of these problems and then I can repeat it a second time on Thursday. Let's do pop front. So it's supposed to remove the head node, and by that what it means is destroy the first node in the list. In other words, delete it. So let me change my picture. It's helpful, by the way, to sort of imagine a couple of different scenarios when you're developing these. And I'm going to imagine 3 different scenarios. The first scenario is there's nothing to destroy, which would be a problem. The second scenario is there's only one thing to destroy. And the third thing is there's 2 or more things, and I want to destroy the first one. So the whole point of this function, pop front, is to get rid of this first one. But I want to see if there's any difference between, I know this one's different because there's nothing to remove. But there might be a difference between destroying the first thing when there's no other things and destroying the first thing when there are other things. So I just want to keep that in mind. But if you take this one as an example, what should be true after this function is over, if this is node 2 and node 1, if I pop front on this one, what the list should look like when I'm done is this. This 2 should be gone, and I should be back to just having the number 1 as the first thing in the list. So I have to be careful of that. Okay, so the pop front is easy when the list is empty, because I just throw up my hands and emit an exception. I can't pop the front when there's no node there. The second one, we'll just see what happens, but this is how I usually do it. Grab yourself a pointer. So I'm going to make a temp pointer that points at. So the equals sign is, I think, easier to understand when you're talking about pointers if you read it as the node pointer called temp points at what? It points at what the head points at. So if I use this first picture, temp points at the same thing that head points at. That's all that code means. Temp points to the same place, temp equals, temp points to the same place that head points at. So now they're both pointing at that node, and we should feel sorry for that node because it's about to be destroyed. Okay, then what I do though is, and it might be easier to imagine in this case, I'm going to point temp to number 2 and head points to number 2. So before I destroy number 2, what I want to do is move the head over 1. So that I end up at the end with this situation. So I need to move the head over. So in code that looks like this list heads now points at the next one over from head. So this head points to the same thing that the next one over points at, which effectively shifts head from where it is to the next one over. So this head is now moved to the next one over. Temp, by the way, is still sitting here on this poor bastard who's about to be destroyed. So now I'm going to use that temp to destroy that node. So I just destroyed this node and basically everything about it. So I just deleted it. Temp I don't really care about. That'll just sort of go away with the function. And what I'm left with is exactly what I wanted, which is head pointing at the next one over. The only thing I need to be careful of here is that I adjust the size down by 1. Because I just destroyed a node, so that's 1 less that I'm managing. I have a Wacom tablet, I just haven't got it working, by the way, so hopefully these pictures will get better, but I got to work on that. This is not easy. It seems like it when someone else is describing it. Oh yeah, it makes perfect sense. But writing this code for yourself is quite difficult. I can't recommend highly enough trying to draw pictures. And as you write a piece of code, try to draw a picture of what that code means. I'll give you an example real quick. So if I write the code, node star n and with value node null pointer, the picture I would draw of that would look like this. So to draw pointers, I use arrows. So that's the picture of that code. Now if I were to say n equals new, so I'm going to dynamically allocate a node with some value in it, let's say 10. What does this mean? Well, it means that n now points at, n, which is a pointer, now points at a dynamically allocated node. And I know that nodes have a place for data or a value, and nodes have a link pointer that is called next. The value goes in here. So n now points at a dynamically allocated node that holds the value 10. Now I know that the node constructor takes that 10 and stores it as its value. And then I also know that the node's constructor nulls out that link pointer. So at the end of this code, I have n pointing to a node that contains a value and has a link pointer that goes to nothing to start. I wish I had saved. Okay, I'll just have to redraw it. I went slightly too. Okay, so closing thoughts here, kinda. This is where we left off with n equals new node 10. Made this drawing. So now let's think about what happens if I say this. Star t equals n. So t can point at a node, and it points at where n points at. T points at where n points at, is how you kind of read this as pointers. So t points at the same place that n points at, which means that n and t are basically, they're the same node. At least right now they are. So try practicing this, and try practicing it just with simple. They may not seem simple at first, but without too much code to mess with your head. Just little things. Yeah, if I don't have a non-porous surface, that's convenient. But I do have a Wacom tablet, so I'm going to try that eventually. It just, you can't go anywhere here and like buy stuff that easily, and I get counted like a criminal when I go to Target or Safeway. They count me on the counter, which freaks me out because I don't want to live in Hitler's Nazi Germany. Anyway, so try this with small stuff, and if you can get in the habit of drawing these little pictures, it can help a lot when we get to more difficult algorithms. Okay, so I'm gonna stop there. On Thursday, I am not going to redo any of the Lab 10 work. I'm just going to redo I'm just going to do all the things for Lab 11 that are needed. So just heads up about that. I'm assuming that you have Lab 10 from last week, and I'm only going to fill in code for Lab 11. This pop front is a Lab 11, and I'm going to redo that on Thursday. So if you don't have it today, I'm going to go through the whole thing again on Thursday. All right, other than that, I'm going to now stop talking, and I'll field questions for a few minutes if there are any. Okay, so I'll be here in the morning at 10 for just question and answer session. And then if I don't see it tomorrow, I will be back at 11 on Thursday. Have a good day.